In our previous lesson, we talked about acid-base neutralization reactions, and we learned how to locate the equivalence point graphically on a titration curve. Today, we're going to do a second part to this, where we're actually going to calculate the equivalence point and determine it mathematically. So here's a typical titration question at equivalence point. So calculate the pH at equivalence, and remember what that means. That is telling us that the moles of acid and base, my two reactants, have to be perfectly equal according to the mole ratio. Okay, so we will be aware of that. So we're going to take 25 mils of ammonia. Let's get our reaction ready right here. We're going to react it with HCl. And here we are with ammonia, no hydroxide ion in it. So we're just going to combine everything and get ammonium chloride. So we know that we have 25 mils of ammonia. We're doing some stoichiometry, so it's always good just to write what you know beneath each substance. A concentration of 0.2. And then we know that the concentration of HCl is 0.25 molar. Now, they don't tell us the volume of HCl that was added. And you're going to notice here that the first step says to calculate the unknown volume of the acid or base. Often these questions will want you to calculate that, and we need it because initially or eventually we're going to have to calculate the concentration, the molar concentration of my salts, and that molar concentration will be dependent on the volumes of both acid and base. So the first thing that we want to do is calculate the unknown volume of, in our case, this is now going to be an acid. So we don't know what this volume is. So we're going to use some stoichiometry in order to do this. Step one, we might as well calculate the moles of ammonia because I have both of those variables, and I have to take molar concentration times the volume in liters. So my concentration is 0.20 molar. My volume has to be in liters, don't forget, so we're going to convert to 0.025 liters. And then we get a mole value of 0.0050 mole. Try to maintain at least 2 sig figs here. The calculator will chop it after the 5. Now, everything's a 1-to-1 ratio. So when I mole ratio over to HCl, my moles of HCl are going to equal my moles of ammonia, because of, again, a 1-to-1 ratio, which is a nice thing. And so my moles of HCl are exactly the same, 0.0050 mole. And this makes sense, right? This is what equivalence point is. We should not have any leftover acid or base here. But I need to find the volume of acid that they added. So step 3 will be just a quick conversion of figuring out the volume of HCl using our mole formula. So we need to take moles divided by the molar concentration. And we're going to take 0.0050 mole, and we're going to divide it by the molar concentration of 0.25 molar. And I get a volume of 0.020 liters. Okay, and I need that because, again, we're now going to be asked to calculate the molar concentration of my salt. So once again, I look at this stoichiometric relationship. Everything's a 1-to-1 ratio. So the first thing that I want to do is figure out the moles of ammonium chloride. And because everything is a 1-to-1 ratio, it's going to be exactly the same as the acid and the base. So we're just going to always write that in due to 1-to-1 ratio so that I know you're looking at those coefficients and making that judgment. So then we want to do our molar concentration of ammonium chloride. And in order to do that, we need moles divided by volume in liters, but it has to be the total volume. Okay, it has to be the total of the acid and the base, because after your titration, you've added acid and base together in your Erlenmeyer flask. It's all sitting there. So we're going to sub this in, so 0.0050 mole. And my total volume is this 25 mils from the base and this 20 mils from the acid. So we're going to have 0.045 liters there. And then when we divide that out, we get a molar concentration of 0.11 molar. Okay, so nothing too new here. Is there some stoichiometry moving around trying to figure out volumes, moles, molar concentration. But we need this so that we can go on and take this salt and now determine the pH of the solution. So now we're going to take the ion of the salt that came from the weak acid or the weak base and write out a dissociation equation for it. So the ammonium ion is the ion that we are most interested in. It came from the weak base ammonia. And this ion is the conjugate acid. So acids are proton donors. A hydrogen is going to get released over to the water molecule, hydrogen bond to create hydronium. And then we're left with the ammonia ion. We're going to set up an ice chart here, and we have our initial concentration of the ammonium ion. So remember, we calculated that the concentration was 0.11 molar for the ammonium ion, and this is a 1-to-1 ratio of ions, so it stays the same. We still don't care about water. Initially, we don't have any of my products. And then over time, because everything's a 1-to-1 ratio with acid-base chemistry, we're going to lose some concentration of reactant in the form of X. Those products will both gain it. And then at equilibrium, we have 0.11 minus X for my reactant, and we have X and X for my products. So we're going to set up a Ka expression, right? Ka because the conjugate the conjugate acid is producing hydronium ion. So we're going to have the concentration of hydronium times the concentration of ammonia all over my conjugate acid, which is the ammonium ion. Now, the Ka for ammonium ion is likely not in your chart, but you know what to do. You can use our relationship. So we'll just come back over here. Let's get rid of that. And let's calculate our Ka of the ammonium ion using that relationship of Kw divided by the Kb of the acid or the base. So this is the Kb of the ammonia ion. When you look up the Kb of the ammonia ion, which is 1.8 times 10 to the negative 4, we're going to set this up. Kw is 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And we get a Ka value of 5.56 times 10 to the negative 10. So we're going to set that up over here, and we're going to solve for X. So 5.56 times 10 to the negative 10 is equal to X squared over 0.11 minus X. Now, take a look at your K value. Okay, 10 to the negative 10, really small. You need to show me on a test that you are checking for small K, but we know that is going to be allowing us to neglect X, which is a good thing. We rearrange everything. We take the square root. You're going to get an X value of 7.82 times 10 to the negative 6 molar. And this X term is for hydronium. So if we want to calculate the pH, we just need to take the negative log of that hydronium ion and sub it in, 7.82 times 10 to the negative 6. And then we get a pH value of 5.11. So again, this is how we determine the pH at equivalence through calculation when we don't have a graph that we can visually take a look at the equivalence point graphically. Another type of titration calculation we can do is when we haven't quite reached the equivalence point. So here's an example where we're going to calculate the pH if 10 mils of 0.35 ammonia is titrated with 30 mils of 0.25 molar HBr. So notice that the word equivalence is not here. So this makes us very suspicious that we are not at the equivalence point, and we're at a point in the titration where there's an excess of one of these reactants. And we can figure out who that would be, and they will be influencing the pH of the solution at this point. So as usual, we just jot everything down that we know under our substances. So this is 10 mils of 0.35 molar ammonia, and then we have 30 mils of 0.25 molar HBr. So normally we are interested in the salt, but right now we're going to check to see if one of these reactants is limiting and one is in excess. Then we know that the titration is not completed, or the neutralization reaction is not completed. So the first thing that you have to do is figure out the moles of each of your reactants. So we'll set it up for ammonia first, and we're going to take concentration times volume. And we have 0.35 molar. Again, make sure you convert your volumes into liters. So our moles of ammonia work out to be 0.0035 mole. And then we'll do the same thing for HCl. So HCl, same thing, concentration times volume. What do we have here? 0.25 molar times 30 mils, which is 0.0300 liters. And we get a mole value of 0.0075 mole. Now, it's not at equivalence point. If it was, those moles of ammonia and HCl would be equal, and they're not. And you can tell that HCl is in excess. Now, the thing is that this 0.0035 moles of ammonia has reacted away some of these HCl molecules. So we want to calculate the excess amount of moles of HCl that is currently remaining. And in order to do that, we take the mole value of it, 0.0075, and we subtract off the moles of base that have reacted away with some of the HCl molecules. So what we have left over is 0.0040 moles in excess. And then we're going to take that excess amount of moles and we're going to figure out the new concentration of HCl, because remember, they're asking us to solve for the pH. So we know it's going to be an acidic pH. We know that HCl is in excess. So we want to figure out the molar concentration of HCl, again, by taking moles divided by volume. And our moles are 0.0040 mole. And that volume, again, has to be a total. So we've just combined 10 mils of ammonia and 30 mils of HBr. So my new volume is 0.040 liters, or 40 mils. When I divide that out, it's an easy calculation. I end up with a molar concentration of 0.1 moles per liter. And now I have to calculate the pH of the solution. So once again, we recognize that HCl is a strong acid. And if it's a strong acid, it's 100% dissociation. And so that HCl is going to break down 100% into hydronium and chloride ions. So if this is 0.1, so is this 0.1. We don't have to set up a nice chart here. It's a straight dissociation. So the pH is equal to the negative log of hydronium, which is 0.1. And so if I take the negative log of 0.1, I actually get a pH of 1.00 for this particular solution. So again, just a twist on a titration, using some stoichiometry to determine the pH of our solutions.